So in this video, we're going to talk about what weight actually is. It's a term that gets used really often in the English language, but gets used in the wrong applications in physics terms pretty often. So let's consider a couple different things that might be said that have the word weight in them. Somebody might talk about their weight and say that they weigh 71 kilograms. That's what the doctor would say if you went there. Well, they wouldn't say 71. They'd say whatever your weight is. They'd say you weigh blank kilograms. Doctors tend to use kilograms more than pounds these days. But yeah. Then you might also hear somebody say, okay, well, I would actually weigh less on the moon, or I would weigh more on Jupiter. Um, and again, I'm sure you've heard this. Or somebody would say, hey, I was on a roller coaster and I felt weightless. Or somebody on the space station is weightless. Or if you're in an airplane that starts going straight down, you feel weightless. And the last thing to consider is somebody who says, oh, a bathroom scale, that's for measuring weight. Or you think that, probably don't say that out loud. It's kind of a weird sentence. These are all different sayings or different topics involving the word weight, but actually only one of them is using weight in its correct physics context. Let's go through this. Let's define some important terms, starting with what actually is weight. So weight is it is quite simply the force of gravity acting on an object. That means that force of gravity is equal to weight, which is equal to mg. That means weight is always going to be accurately measured in newtons because it's a force measurement, nothing else. Which means that if you've heard somebody say, or people talk about they weigh 71 kilograms or whatever, that's an incorrect statement because that's not actually talking about weight. What that's talking about is it's talking about somebody's mass. And mass is the amount of stuff. It's the amount of stuff you're made of. It's how many atoms, how many protons, neutrons, electrons, and the sum of those things together that you're made of. And it's actually more complex because there's bonding energy that contributes to your weight and all kinds of things like that. But the mass is how much stuff is in you. And mass is going to be measured in, well, we always use the variable m to represent it, but it measures in kilograms. And there's two types of mass that we need to talk about. We have a mass called inertial mass and a mass called gravitational mass. Inertial mass is what we talked about back when we were doing Newton's laws. It's how much the stuff you're made of reacts to the attempts to accelerate you. A large object has a lot of inertial mass, and it's hard to get it moving, and a small object has the opposite, or tends to. Uh, Gravitational mass is the fact that the amount of stuff that you have attracts the other stuff in the universe. So anytime that you talk about inertial mass, we're usually talking about accelerations, and gravitational mass is talking about attractions to other masses. Every experiment we've ever done has shown that the value of inertial mass and the value of gravitational mass are exactly the same. But the AP exam, for whatever reason, is very interested to see if students understand the difference between the effects that mass has on inertia and the effects that mass has on gravity, which are, even though we've always seen them behave exactly the same, two different phenomena that we haven't been able to fully explain why they're the same. We just know that they are. So going back to some of these statements, if we say that we weigh 71 kilograms, that's not true. You have a mass of 71 kilograms. Because we only do masses of people on Earth most of the time, knowing your mass on Earth is just as good as knowing your weight on Earth. But when we go to that next statement, we weigh less on the moon. Well, that's true because the value for g, the free fall acceleration on the moon, is less than it is on Earth. Your mass didn't change. You're still made out of the same amount of stuff, but its attraction to the Earth or to the moon would be different. What's interesting though is if somebody's trying to knock you over, it's still just as hard on the moon as it is here because your inertial mass is the same. All that's changed is your weight from your being pulled towards the Earth. Okay, so that's weight and mass. Our next thing that I want to just talk about is apparent weight. And apparent weight, let's see, I'm going to pause it real quick so I can write out the whole thing without you guys watching me write. So there it is. Apparent weight is our experience of weight. It's us thinking that we know how much the Earth is pulling on us, but we don't. What we know is how hard the surface of the whatever we're on pushes against us, and we're sensing not our pull towards the Earth, but our push on the objects pushing against us. So when you think that you feel weightless on a roller coaster, yeah, it's not realistic to say that like, okay, the Earth is no longer pulling on you. You're obviously not weightless. What's happened is you're no longer feeling normal force because the roller coaster is falling out from underneath you, and so you feel weightless because you no longer feel the apparent weight from the normal force pushing on you. The same thing happens with a bathroom scale. Bathroom scales are nowhere near sophisticated enough to somehow measure the gravitational attraction between us and the Earth. They just figure it out uh, by looking at what the normal force of us pushing on them is. And then they assume that we're at rest and we're staying there, and so it must be true. But you know you can defeat a scale. All you have to do with a scale is jump on it or jump off of it, and you would notice that the reading on the scale would change drastically. Not because your weight has changed, but because the normal force being applied on the scale from you has changed. You could also trick a scale by standing on it in an elevator. And if the elevator is accelerating upwards, then the net force acting on you would be upwards. There would be a normal force that's greater than normal acting on you, and so the scale would say you were heavier. But if you were going the other way, you're on a elevator, and you've probably experienced this, and it starts going down. You have that weird feeling in your stomach, but also the scale's falling out underneath you, and normal force would be slightly less at that time because your net force is down, and suddenly it looks like you weigh less, but you don't. So going on elevators doesn't magically change your attraction to the Earth. It just changes for moments the normal force that you're experiencing. So that's what apparent weight is really all about. And so if you're ever asked a question about the apparent weight of an object, they're not asking about weight. They're asking about normal force, which is still measured in newtons, but they're looking, when you're doing your free body diagrams or your force equations, you're solving for a different piece. So hopefully that helps you understand now what weight is.